Hi everyone. Today I'm going to discuss some more important properties of a matrix. Okay, if you have seen my previous videos, you have almost completed this chapter, I think. These are basic concepts. My future plan is that I will explain several other things, that is not things, actually I'm going to solve lots of problems from this chapter, which is also going to cover your jam problems. Okay, previous year problems especially, not only previous year. I am going to solve many problems from this chapter. Mainly, let's see how many problems I can solve. Also, you have to complete the syllabus in time, so maybe 10 problems to 20 problems or more than that, I don't know, because the problems are very important. Ultimately, you people need to know how to attack a problem in the examination field, right? It's like a battle. So that is important. So problem solving skills is more important than anything else. Sorry to say, but it is more important than concept. If you know a formula and you don't know anything regarding that, but applying the formula, you can solve the problem. So problem solving technique, that technique you people need to grab. Okay, and after completing mathematical physics completely, I also have many problems from all the chapters, and that is very important. Okay, maybe 50 problems from everything or more than that. Okay, I will solve many problems for you, so watch it carefully. So most probably this is the last video, and it might be a little bit long, 20 minutes plus, or can be a little, I don't know. It might be long. Okay, I'm not going to extend it more than 25 minutes. It will be less than that. Okay, so I'm going to teach you what is left, some important properties of matrix, part 2. So first we are going to learn today is diagonalization of a matrix. Diagonalization of a matrix. Diagonalization of a matrix. So suppose a matrix is given. Okay, suppose the matrix is A. We need to diagonalize the matrix. So what is the basic formula for diagonalization of the matrix? It is equal to D is equal to P inverse AP. And A is the given matrix and P is known as the modal matrix. What is modal matrix? This things will not come, but these forms are important. Kindly remember the forms. I'm not going to solve any problem for this. These are going to take pages and pages. You need to find inverse, you need to find eigenvalues, eigenvectors. From that you need to find, you need to write the eigenvectors in a column, which is known as modal matrix, and so on. Okay, I am teaching you this. So what is modal matrix? Suppose we have a matrix given A. Let me consider a 3D matrix. Okay, so yeah, so when we can find three eigenvalues. Okay, might be distinct or indistinct, it doesn't matter, but we'll find three distinct eigenvectors, as eigenvectors are unique. So we'll find x1, x2 and x3. I hope you remember what is eigenvalue and eigenvector. I am not repeating it. Kindly watch my videos if you are not so comfortable here. So you people need to find the eigenvectors. Okay, they are always in a column, you know. What is modal matrix? Modal matrix is nothing but this, I mean, cumulative expression of these eigenvectors. This is x1, this is x2, this is x3. This is the first eigenvector, this is the second eigenvector, this is the third eigenvector. How do you write eigenvectors? Suppose this is k 1 2. Suppose x2 is 2 3. Suppose it's 3 dimension, right? So yeah, you have 3 values. Suppose this is 0, this is 0, and you have 2 2 3, like this. K value should be there. So what is the modal matrix? This one. And please start with the lambda value which has the smallest value. I repeat, start with the smallest corresponding eigenvector of that eigenvalue which has the smallest value among all the eigenvalues. Okay, so the first one will be 1 0 1 2 2 3. Actually this is x2, right? So 2x 230 and 223 223. So this is the modal matrix. Now it is clear to you. So D is equal to P inverse. You need to find the inverse of the matrix. You have that matrix and you have P, the modal matrix. So this is how you can diagonalize a matrix. Okay, let's go to the next property. In my previous video I have discussed how you can find power of a given matrix by Sylvester theorem. There is another form which is a to the power n is equal to p d to the power n into p inverse. Okay, this is how you can also find power of a matrix. This is a very big process, so don't follow it. Follow Sylvester theorem, but kindly note down the point. That is, this form is also possible from modal matrix. Don't miss any form. Okay. Okay. Let's come to one thing that do you know what is a similar matrix? Similar matrix. Similar matrix. A matrix which has the same eigenvalues. Suppose there are two matrices A and B. If they have the same eigenvalues, that is the trace of, that is sum of the diagonal elements of the two matrices are equal. Okay, these two matrices are known as similar matrices then. So suppose A is a matrix and B is a matrix. We find the characteristic equation. As you people know how to find it, we find the values of lambda and found that both the matrices are given the same result, that is A, B and C. Both the matrices have similar eigenvalues. Also the sum of this eigenvalues equalizes the trace of the matrix, so that is also going to be equal. So this type of matrices are known as similar matrices. Hope the concept is clear to you. So let's go to the next part. Suppose you have a matrix A and which is multiplied with its transpose and gives I. What is the name of this matrix? Tell. Yes, orthogonal matrix. Orthogonal matrix. Remember a property, if lambda is an eigenvalue of this matrix, then another eigenvalue should be 1 upon lambda. Okay, if there is a lambda, there will be a reciprocal of lambda as the eigenvalue of the given matrix if it follows the orthogonality principle. Okay, easy. Okay, make a rectification of this thing. You can find in some test series. Any square matrix, let me pause the video and write, that will save time for both of us. Okay, so the statement says any square matrix R can be proper rotational matrix if and only if R is orthogonal and mod of R is equal to 1. Okay, this is the statement. I can make you understand this. Sorry. Eigenvectors corresponding to non-degenerated eigenvalues of the orthogonal matrix will be orthogonal. Again, I need to pause. Let me write. I will make you understand this. So what is the statement? Eigenvectors corresponding to non-degenerate eigenvalues of an orthogonal matrix will be orthogonal. Suppose non-degenerated, right? Non-degenerated means lambda 1, lambda 2, lambda 3. These are non-degenerated. So nothing equalizes nothing. This is the main point. Lambda 1 does not equalize to lambda 2, and lambda 2 doesn't equalize to lambda 3. So this is the main funda. If you get corresponding eigenvectors to this, if it is an orthogonal matrix, the eigenvalues you people are getting from an orthogonal matrix. That is the main point here. Okay, vectors corresponding to non-degenerate eigenvalues of an orthogonal matrix. This point you people need to remember. If it is from an orthogonal matrix and you people are getting this lambda values from an orthogonal matrix and the corresponding eigenvector, suppose xi, x2, x3, then this three are orthogonal to each other. That is, this law will be applicable, and so on, x2 transpose x3, whatever you take. So this law will be valuable. Okay, so this is the case. Let me see what properties are left to teach you. I have gone through this. Remember one property what I told as Hermitian, that A B theta or dagger, what people you are comfortable in or what your professors are teaching, you may follow that. I follow theta, but my professors use this. I don't care. So B theta, A theta. This is the case. Okay, write a very important concept. This question might have come in CSI and net, I think. I don't know in which year. Whatever, leave it. A real 3x3 matrix can have 3 real eigenvalues or one real eigenvalue with 2 complex eigenvalues conjugate to each other. So what is it saying? Yes, so 3 real eigenvalues, sorry, a real 3x3 matrix can have 3 real eigenvalues or one real value with 2 complex conjugate eigenvalues. Okay, so what it is saying is that there is a real matrix, all real entities are there. You may get lambda 1, lambda 2 and lambda 3, which corresponds to real values only, or you can get this as 2, and suppose you get lambda 1 equals to 2, lambda 2 equals to 5 and lambda 3 equals to 6. You can also get this as 3 iota but the lambda 3 you will get minus 3 iota. This is the theorem saying. This is what the theorem is saying. Okay. This is only applicable for real matrix. The entities are real, not Hermitian or like that. Okay. Okay. So you would remember what is a unitary matrix. Suppose there is a matrix A multiplied with its transpose and conjugate will give you the identity matrix. Then the matrix A is known as unitary matrix. Okay. It is saying that the mod of each characteristic root. What is the characteristic root? It is the eigenvalue. It is the eigenvalue, the value of the lambda you are getting. That is eigenvalue. If you take the mod, you will get unity. The mod of the characteristic root of a unitary matrix is unity. Okay. Next is, I told you that orthogonal 1 lambda and 1 upon lambda. If the characteristic equation are equal, then the eigenvalues are same for both. Obviously, if, let me pause again. If the characteristic equation are equal, then the eigenvalues are same for both. You understand? This is the equation. This is another equation. You get the same eigenvalues. Bogus property. Okay. You know this. You have studied this in class 12. And obviously, in general case, x and x inverse is equal to x to the power 0 equals to 1. I told you what is 1 in general case equals to identity matrix in matrix case. So, this is the answer. Let me check any other properties are left or not. Yes. I have told you this, let me repeat that the eigenvalues of a Hermitian matrix is real eigenvalues of a Hermitian matrix are real. Okay. And what is for A? The mod of characteristic root is equal to 1 in case of unitary matrix. This is for Hermitian matrix that eigenvalues will be real. Remember this. Okay. For skew Hermitian, the characteristics roots of a skew Hermitian matrix is either 0 or purely an imaginary number. So the characteristic roots of a skew Hermitian matrix, you know what is skew Hermitian? Opposite of Hermitian. That is A is equal to A theta, transport and conjugate of A, both equalizers. Here, in case of skew Hermitian, A is equal to minus A theta. Okay. So the characteristic root will be 0 or purely an imaginary, not complex. You know what is the difference between complex and imaginary? a plus I beta, this is a complex number. It will contain a real part and an imaginary part. What is imaginary number? This part is only imaginary. So eigenvalues will either be in this form or 0. This is for skew Hermitian. If you multiply, suppose A is Hermitian, if you multiply iota with A, it will become a skew Hermitian, and vice versa. If A is skew symmetric, if you multiply iota with it, it will become Hermitian. Okay. Every square matrix can be expressed as R plus IS, where R and S are Hermitian matrices. Every square matrix can be expressed as R plus IS, where R and S are Hermitian matrices. Okay, so every square matrix can be expressed as R plus iota S, but R and S are Hermitian matrices. Not so important. Same for a case, Hermitian and orthogonal. That what you say is that you can express a matrix in terms of sum of symmetric and skew symmetric matrix, and similarly Hermitian and skew Hermitian matrix. This A can be written as, this part is symmetric matrix, symmetric, and plus this part is antisymmetric. You know this from class 12. Skew symmetric, skew symmetric. And also you can define this matrix as the sum of Hermitian and skew Hermitian. A plus, this is Hermitian part, plus half of skew Hermitian part, skew Hermitian part. Okay, so I have taken many pages, right? Oh my god, 37. Some are blank, I think 1 or 2. Okay, so nothing is left to teach you on this part. I am not going to cover the determinant part or rank of a matrix like this. I am not going to cover, they won't come. So yeah, this is the end of matrix chapter. It's more than enough for IIT JAM Physics. Now our target is to learn lots and lots of problems. Oh my god, what's this? Yeah. So that will be helpful. Already I told you it will be nearly 25 minutes, and it is. Also I have paused some in between for writing this stuff so that it doesn't waste your time. Okay, thank you everyone for watching the video. Hope the concept is clear to you. We'll meet again in the next video. So tata, bye, have a nice day or good night. I don't know in which time you are watching this video. Okay, thank you.